This is a talk of an introduction to monads, and this talk aims to introduce functional programming patterns in F sharp. Just a disclaimer that this talk may potentially contain error. If you are a Haskell or a functional programming expert, please let me know. My name is Haibin. I'm currently a data engineer at a hedge fund. I have a master's degree in mathematics from University of Michigan. I was previously working as a financial engineer at Numerical Technologies and as a business analyst working at US Mattress. So we'll start off today's talk with just this very basic simple code. Let x equals to 2 plus 3. Of course, you know that this would give you x equals to 5. That is obvious. But now I want to introduce a different notation that we will use throughout this talk. It is the data extraction form. So you take a look at this code, let exclamation mark, let bang, a equals to x. You take a look at this expression, and how should we interpret this sentence? How should we interpret this code? We should think of this as the following. The x on the right hand side, you should think of it as a box, like a bigger box, and inside the box there's a small there's a toy inside, there's a content inside it. And this a, you should think of it as the content inside the box. So when you see this expression, you should think x is a box and a is the content inside the box. Again, when you see an expression like this, you should think of x as the box and a is the content inside of the box. And also, when you see an expression like this, you should also have something in mind that we are doing more stuff in the background. There are actually more things going on than just extracting something out of a box. So you see a code like this, you would first think I'm extracting something, some content out of a box, and also I'm doing some extra stuff in the background of this code. So when you see this code, you should think I'm extracting a out of a box x. In addition, I'm doing extra stuff in the background as well. So you take a look at this basic code over here. Let W be the result of all of these code. So you take a look at the result of this chunk of code. It should give you 6. A is 1, B is 2, C is 3. The sum is 6. So W is 6. But for our case today, we will see a code that looks like this. Let W be the expression of all of this expression. When you take a look at this, you should first think that we are doing an extraction process in the middle, just like we have mentioned just now. We are doing an extraction process, but also what is also important is that we are doing this extraction inside a certain environment or a certain class. We are doing the extraction process inside a certain class or environment, and that class or environment will determine what are the background process that goes behind the extraction process. So this is the main pattern that we will repeat throughout this talk today. So again, we are extracting a content out of a box, but what is also important is the environment that we are executing our code, that we are extracting our content from. If you are using a Haskell-Style syntax, you may use like a symbol like this, which again, you are trying to start with a box and you extract out the content out of it. And so this symbol over here represents both the extraction process and handling special case in the background. If you are using a C# style syntax, you may see a syntax that looks like this. Then again, you are starting off with boxes XYZ, and you extract out the content ABC, and we are performing operation on ABC. So with that, this is the syntax that we will work with throughout this talk, this syntax over here. And with that, let's get to some examples. So the first typical example of monad is the option type or the nullable type. Basically, it is used to handle cases where data is missing. For example, you have a box here that is empty inside. The box is empty. So how do you handle cases where there are empty data? So you take a look at this code. X is the calculation of formula 1, formula 2, formula 3. And you calculate the result by adding up 3 of these values. But there's a problem here. What happens if X is null? Maybe the result of X is missing, or there's no result. What will happen? In C#, we typically use null to represent missing values. But null comes with its own set of problems. One is that you are unable to determine when a data is missing. Is a data type potentially be null or not? And it makes code, and you may need to do like null checks. You need to make sure that your data exists. It makes your code a little bit difficult to write. Tony Hoare even called it the billion-dollar mistake when he designed the language C. In F#, how do we handle potentially missing data? We use the option type, which it's either some or none. We'll do a demonstration or an illustration. Let's say that x, y, z is 1, 2, 3. What is the value of x plus y plus z? Of course, it's 6. But if, let's say, one of the value is null, one of the value is missing, how can you define x plus y plus z? How can you define this? You would define this as null. You would define this as missing as well. Since one of the data is missing, so you cannot add them up. So this should be reported as missing as well. So if you want to write a code in C#, you may need to check for null value, check for null value, check for null values, and then you can do this calculation. Otherwise, you may need to return null early. So this code looks a little bit messy. It's doable, but messy. You get a triangle shape over here. If you have more null values, then you need to go even deeper into the indentation. In F#, we can write a code that looks something like this, where, just like we said before, we have x is a box that could potentially be missing value. We want to extract a value out of a box x, where x itself could potentially be missing a value. We extract a value a out of a potentially missing value x here. And the environment option type, the environment here, helps us handle the edge case or the missing case. If, let's say, any data in between is missing, then it will return null, return like missing none in the end. Let's take a look at another example, which is the result type or the exception. The analogy is this jack in a box or clown in a box. You have a box, you want to see what's the content inside that box, but maybe if you open the box, a clown will pop out of the box, which is not what you have expected. And it is similar to our situation in our code. In C#, we use exception to represent errors. So it's a perfectly fine way to do programming in C#, but there is a couple of problems with this style of programming. One is that your exception could potentially be thrown anywhere. So if, let's say, you have some programming code that you expect to return an integer or something, and suddenly it throws an error message or an exception. So it makes your code less reliable. There could be errors or exception appearing anywhere. You could potentially need a lot of try-catch statements in order to handle all those error cases, which could make your code look a little bit messy. So you take a look at this code over here. You calculate A, B, C, then you add up A, B, C. But every single point of this function could potentially fail, could potentially give you an error. So where's the error? Just from this code, you cannot really determine where's the error. If you want, you can prevent any errors by doing a try-catch statement right here, where in this try-catch statement, if you see an exception 1 or exception 2, etc., then you handle each different case individually. Alternatively, you can try this method instead. Maybe each function returns a value and an error message. Only if so each function contains a value and an error message. Only when all three error message is okay, then I do my calculation. If there's some other error message that is not empty, then we need to do something else. You can certainly write your code like this, but it will also make your code a little bit messier. So let's analyze the situation. If let's say you have three numbers, 1, 2, 3, you want to add them together, what is your expected result? You expect to get the number 6. However, what happens if one of your calculation returns an error? How do you add up A, B, C, X, Y, Z? The answer would be the error message, because one of them gives you an error message, so you keep the error message as the result. What if two calculation returns an error message? What should you do? In this case, you return the first exception or the first error that is encountered. So that if let's say your calculation goes to Y, then it doesn't even proceed to Z. It will just stop at Y and immediately return Y. In F# code, it will look something like this. Notice that in this code, I have a value here A that is extracted out of a potential error X, and B extracted out of Y, C extracted out of Z. This is a valid F# code, and the environment here, the result type, the environment here will help us handle any potential errors. If we encounter an error, we immediately abort the calculation and return the error itself. Let's take a look at another example, which is the list type. This should be familiar to any programmers programming in a for loop manner. So let's say that I have a list 1, 2, 3 and another list 10, 100. How should you define X multiplied by Y? There could be many different definitions, but maybe something similar to this would be helpful. So I take each element in X, I take each element in Y, and I multiply, and it gives me a longer list. So I have 3 elements here, 2 elements here, which multiply to give me 6 elements in X times Y. In C#, you can write a code that looks similar like this. For A in X, for B in Y, you calculate A times B, and you add them to an accumulating list here. So this is how you would write a code in C#. In F#, it is possible to write it in such a way where you extract out individual value out of a list of values, and then you perform operation on these individual values. So this is a valid syntax in F#, and the list environment helps you concatenate all your results into one big list. So this is the environment that is handling things in the background. Let's take a look at another example, which is the logging type. Let's say that you have this calculation a, b, c, and you want to write what is a plus b plus c. But maybe you want to add some additional logging or printing in the process. So for example, after each calculation of formula 1, formula 2, formula 3, you want to write what's the value of a, b, c throughout your process. This is perfectly valid, but it causes a lot of boilerplate in your code. You need to repeat a lot of sentences over here. Console write, console write, console write. It makes your code much longer, much more complicated. So this is our original formula. We calculate what is a, b, c and add them up. In F#, it is possible to introduce the logging environment where you extract out the value or you get the value, but the environment itself does background handling, which means it prints out the information in the background or in the log file. So this is our original calculation. By just adding the environment and some extra exclamation marks, you are able to introduce the ability to log your process, to print out each individual step in the middle. And that's a very huge bonus. You get from here to here by just adding a few symbols, and now you have logging capabilities. Now let's take a look at another example, which is delayed computation. The analogy is like a cooking recipe. What do I mean by that? Let me elaborate. Imagine that you have a recipe X that takes 2 hours to cook and recipe Y that takes 3 hours to cook. We have recipe W that is X plus Y. So you would expect that recipe W would take 5 hours to cook. You just add 2 plus 3. That is easy to understand, but the key concept here is that the recipe W takes 5 hours to cook, but writing down the recipe for W on a piece of paper should not take 5 hours. Writing down the recipe itself should take maybe 1 minute or 2 minutes. To execute the recipe would take 5 hours, but writing down the recipe should not take that long. Similarly, if let's say you have an algorithm X that takes 2 minutes, algorithm Y that takes 3 minutes, and W is X plus Y, then W should take 5 minutes to fully execute, but creating the instructions for W should not take that long. So let's do a demonstration with some C# code. You take a look at here, you execute X, you execute Y, and then you calculate their sum. This will take 5 minutes because X takes 2 minutes, Y takes 3 minutes. So executing this formula will take 5 minutes. On the other hand, if you define it like this, where W is a recipe that follows this recipe that I've specified here, then W itself is a recipe that is not yet executed. If I want the final result of this recipe, over here at the bottom, I would execute it and save the result to C. When I run the recipe here, this takes 5 minutes, but this recipe specification on top, should take at most 1 second, but executing the recipe will take 5 minutes. This is what it will look like in C#. In F#, it would look like this, where over here on the right hand side, I have a recipe or an algorithm or a formula that I have not yet executed, but I treat it as if I've already extracted out the result and I get A and B. Then I return A plus B. Of course, the delay environment that I've specified, the delay environment would mean that I'm writing a recipe down. I'm writing an algorithm down. I do not intend to execute it immediately until maybe later when I need the final result. So this environment that I'm doing the extraction on knows that I'm writing a recipe, and so it should not take too much time to write down the recipe instead of fully executing the recipe to get the final result. So again, I'm extracting a result out of a recipe or a formula. I treat it as if I can extract such a result, but I'm running this in an environment or a class that is fully aware that I'm writing a recipe or a formula. And so even though in the code it treats it as if I've gotten the result, in reality I'm just writing down a recipe. I do not intend to fully execute the recipe. Of course, this delayed computation is already available in F#. It is called Async. Async is a library that is nicely designed, and also it has more capabilities than delayed computation. It can also do multi-threading computation, multi-calculation. It is actually more than just delayed computation. And right now I want to get to the state monad, but first let me introduce some terminology, some definition. A pure function is a function that gives the same output every time it was given the same input. A pure function gives the same output every time it was given the same input. Let me do an analogy on illustration. You take a look at this vending machine. Each time you put in $1, you press the same button, then a can of Pepsi or a can of drink will drop at the bottom and you get your canned Pepsi. Each time you put in $1, each time you put in the same number, you will get the same brand of soda, you'll get the same brand of soft drinks as your output. Each time you give in the same input, it will always give you the same output. On the other hand, there's a tourist attraction in Seattle, the mystery soda machine in Seattle, where in the soda machine, the vending machine has a mystery button on it, where each time you put in $1 and you press the mystery button, each time it gives you a different can of soda, a different canned drink. So each time you put in $1 and you press the same button, it gives you a different result. And so you can think of this vending machine that gives you unreliable result, that gives you random result, as an impure function. It gives you different result each time you put in the exact same input. Why is this useful is that an impure function gives you different result each time, so it makes your code unreliable, because it could potentially throw different result each time. The common example is random numbers. So let's take a look at this. Take a look at this code over here. I call this get double 3 times to get 3 decimal numbers, and I add up 3 numbers together. But the problem here is that each time I call the get double function, I get a different result. So my code is pseudo unreliable, even though this uses pseudo random number. But anyway, the get double gives me a different result each time. And so it is not as reliable as we hope. So how do we write code that is stable in this form? So first, let me do a basic introduction of how the numbers are generated. This is not a safe method to create random numbers. But this is a toy example. I take a number, I multiply by 97, and then I take the last two digits, or modulus 100. So 97 times 97 gives me something that ends with 09. 09 times 97 gives me something that ends with 73, times 97 gives me 81, etc., etc. If you want, you can take out your calculators and verify these numbers. And with this chain of numbers, I can divide by 100 to get me these decimal numbers. And these would be my random numbers. So how is the random number generated? It's that I start with a starting value of 97, a seed value of 97. I calculate the decimal number that I want. I divide by 100. And then I transition to the next starting value, which is 09. With this starting value 09, I can calculate the next decimal number, and I can also calculate the next starting number, 73. And so the get double function is a function that takes an old starting value and it returns two values. One is the decimal random number and another is the new starting value. So the get double function not only returns a random number, it also changes the starting value from old to new. Again, the get double function gives you a random decimal number, and it also changes the starting value. And so in F#, it will look something like this. The code will look something like this. How should we interpret it? Is that we have a recipe over here. We have a pure function that tells us how to extract out decimal numbers and also how to change the starting value. This itself is a pure function, so it always gives us reliable result if we know what is the starting value. If we know what's the starting value, this function always gives us reliable results. But I treat it as if I can extract out a decimal number out of this pure formula, this pure function. So I have this function that gives us reliable values, but it's a little bit difficult to define, because it returns two values. So this get double function returns two values, but I treat it as if I can extract out the random number. I can extract out the random number, the decimal number that I want, and continue with the calculation. And that's the higher level, that's the good part of this style of writing. You can code a hidden state change, which means the starting value changes throughout your code, but it is hidden inside this pure predictable function, and you treat it as if you can extract out a number, a decimal number here. Let's do another example. Let's say you have a mutable list or mutable like a queue or stack. You add three numbers and then you individually remove them from the list S and you add them up. Seems okay, but the problem here is that each step of the process you are getting a different result each time. Maybe the first time you remove from a list, it gives you 100. You remove again, it gives you 20. You remove again, it gives you 3. Each time you call the remove function, it gives you a different result. So this code is not as pure as we hope. So how do we modify this code? So you are given a list. The remove function returns the first value from the list if possible, and afterwards it modifies the list so it keeps the remaining numbers. Again, you start off with a long list. The remove function takes out the first element and it keeps the remaining numbers in the list itself, if it is possible to remove the first element. The remove function takes a list and returns two things. One is the first element and the second is the remaining parts. So this is our original code here. And in F# you can write it in such a form where you are extracting a value A out of a recipe to split a list. So this remove function takes a list and returns two things, the first number and the remaining numbers. This remove function returns two lists. I want the first element, and this expression treat it as if I can get a value out of a pure function. I can get a value A out of a pure function here. And that is a very higher level of thinking that I think is somewhat neat. And I think it's useful to do some thought experiment, like to think about this example more. These two examples. Let me introduce another example, the reader monad. For example, you take a look at this code that you need to pass this logging environment or this dependency all throughout your code. So FGH depends on the logger here, and you need the logger in order to execute and get the values A, B, C. Notice that there's a lot of boilerplate. You need to pass this logging environment all throughout your code. You need to rewrite this again and again. In F# you can write it in such a form where F over here is a function that is still missing one value. It is still missing the logging environment in order to fully execute. But here I treat it as if I can extract a value out of a function that is still missing the logging environment. I have a function fgh that I have not provided the logging environment yet, so it cannot execute. But yet I treat it as if I've already extracted the numbers A, B, C for me to calculate. Maybe in a more real-life example, you'll see an example like this, where F takes in multiple stuff, including the logger, and GH as well. Using the reader monad that we introduced just now, and also a concept called partial application, you can write your code in F# that looks something like this, where over here F is a function that is partially completed. It is still missing the logging environment. You are still missing the logging environment. You are still missing the logging environment. But I treat it as if I have already extracted out the values A, B, C to perform calculation on. I've used some underlines to make it to visually aid this example, to give us a visual help. But just like I said just now, these functions fgh are partially completed. It still needs the last remaining element, but I treat it as if I can extract out the final value out of this partially completed function. And now for the final example, which is IO monad. The analogy is that you are trying to interact with the outside world. You are trying to read inputs and outputs, but on the other hand, you are also worried that the outside world is dangerous. There could be potentially errors or corrupted files, etc. So how should we handle these situations in our code? Let's do a basic example here. So I have file number 1, file number 2, and I try to count how many words are in file 1, file 2, and I return the result. The result is an integer. But here there are multiple problems. One is, if I just hide the code right here and I tell you it's an integer, do you know what's going on inside this code? you don't know whether this code interacts with the outside world or not. For example, does it read or does it write to a file? Does it contact or connect to a database? Does it send any API requests? All of these we do not know just from the type signature itself. We know that the final result is an integer, but we don't know what's going on in the middle. Another consideration is this: you read a file from your file system. What if someone modifies your file? Maybe they change to a different passage, change to a different article, and now each time you run this file, you may get a different result. And so this function is impure. Each time you read the same file, the file could potentially be changed, and so you will get a different result each time you read the file. Just like the example that we have before, it would be great if we could make our code predictable instead of generating different results each time. And also, what if the file doesn't even exist in the first place? Then your code will just throw an error because the file doesn't exist. How should we handle all of these cases in one go? So the three situations: does your code interact with the outside world? Can you infer this information just from the type signature? In this case, I just tell you it's an integer. I don't tell you what's going on in the middle. And also, what if someone modifies your file so that you get a different result each time? And thirdly, what if the file doesn't even exist? Does it throw an error? And so this is our original code. And you can write the I/O monad or the I/O environment like this, where you take a look at this code over here. You are extracting a value out of a recipe to read from the outside world. So you have a recipe to read from the outside world. You read from a file. Maybe the file will be different this time. Maybe the file doesn't exist this time, but you treat it as if you can extract a value out of it, the content of the file, and then you perform calculation using the content. So you extract out the value out of a recipe to read from the outside world, and the environment, the I/O environment, will help you handle all special cases. So how does this help us in some of our previous situation? So we take a look at this code over here. I hide the information inside this bracket. I tell you that the type signature is I/O of integer. So I tell you that the result is an integer hidden inside an input-output, an I/O box. The result is a special class or a special object wrapping an integer. So which makes it very likely that whatever code that I have right here is interacting with the outside world. I don't need to read what's going on in the file. I just know this information just by looking at the type signature. I know that it is an I/O of an integer. Immediately, I believe that this code is most likely interacting with the outside world. I figured this out just from the type signature without even reading the code at all. And also the code environment, which is I/O, will help me handle changing values or missing values as well. So that is also a huge plus. It gives me predictability and reliability in my code. So just a summary, we have gone through all these 8 different cases: missing values, null values, errors and exceptions, nested for loops, logging and printing, delayed computation and async, changing values, dependencies or loggings, and also I/O. All of these cases, they may be separate from each other, but they could be linked together using the same pattern, which is this pattern, data extraction pattern, let bang a equals to x, which you are extracting an information out of a box, and in addition you are doing some extra stuff in the background. all of these 8 cases here are linked together by the same pattern, which is to do an extraction out of a box and handle extra stuff in the background. And that is an introduction to Monad in F#.